Okay, geometry. We're solving any triangle yet. But as I told you in the last video, when we use law of sines, we end up with those tricky spots, specifically when we're given two sides and an angle opposite one of those two sides. We're going to talk more about that in this video. Okay, so we were talking about the law of sines, and we refer to this as being the ambiguous case when we're given a side-side angle situation. And here's the reason why it's a problem. Let's say I had an equilateral triangle. That's what it looks like. But what if it was just isosceles? If it's isosceles, it means that we know that DE and EG are congruent. So angle D is congruent to angle G. Now, if I bring in a side, or just a segment, that goes from E and it crosses the other side of point F, I create something that looks like that. I now have two little triangles in there. And as we know from proving triangles congruent, this side here would be congruent to itself. So now, if I pull those two things apart, I end up with these two distinct triangles where I have, let me go, I can't do it through a highlighter. Let me go through a pen here. There we go. Get away. I have an angle, and then the two sides, and I have an angle opposite one of the sides. So because that's the case, I end up with two different triangles given these side-side angle combinations. That's the problem. So what do we do about that problem when we're given side-side angle? Well, what happens is we end up with three different scenarios that we really have to look at. And the first scenario is, what if the angle that they give us is greater than 90? Well, then I look at the sides. If the side opposite that angle, so if the A is bigger than the B, what happens is I have one triangle. If the A is equal to the B, we have a problem, because there would be no triangle. There's no way. I can't have two sides equal in a triangle and have that angle be opposite one of them be more than 90. That would say I had two obtuse angles. Likewise, I can't have side A be less than side B, because that would say that an angle smaller has a longer side. Okay, so that's case one. So if we're given an angle greater than 90, the side opposite that angle has to be the biggest side. Likewise, if it's equal to 90, the same thing happens. I get one triangle if the side A is bigger than the side B. Now again, if it's equal to 90, the angle is, I can't let the two sides I'm given be equal either, because again, that would say I have to have two right angles in a triangle. And once again, we can't let the side A be less than the side B. If the side A is a 90-degree angle, I mean side A is a hypotenuse, and it can't be the smallest. That leads us down here to our scenario 3, in which the angle is less than 90. And if it's less than 90 and side A is bigger than side B, again, we get one triangle. So in every case that we have, no matter what the angle is, if side A or the side opposite the given angle is the bigger side, we get one triangle. Now here's something that's been strange. So far, if A is equal to B, we had no triangles. But if it happens here, we get an isosceles triangle. If A equals B, we have an isosceles triangle, which makes it extremely easy to solve, because now we automatically know two angles, and that means we know the third angle, and we're just like booming right there. So that's an awesome case. The last one, if A is less than B, we have a problem. This case is where our two triangles end up from here. This is when this happens, is when the side opposite the angle is less than the given side. And that's the case here. When we look at this isosceles triangle, EF is shorter than either DE or GE. We can see that easily. So that's when we end up with our big problems. So what happens? Ooh, I got a case missing. I'm missing a case. Let's see if I can find it. Oh, I'm missing a case. Oh, there it was. Okay, it's back. Put it down there. Nope, still missing a case. Okay, so I want this to disappear. Good, he's gone. Okay, I'm going to have to write it in. Case 2, I need a better color. Case 2, B sine of A equals side A. Okay, so here's the three cases that we end up with. I apologize for the darker coloring here. Well, maybe I can fix that. Okay, so B sine of A is our issue. Well, here's my case 2. It was in black. Case 2, B sine of A equals A. Case 1, okay, in every one of these cases, we had an angle less than 90, and side A was less than side B. Now, if B sine B times the sine of A is greater than side A, what happens is we get no triangle in that situation. If B times the sine of A equals the sine of A, we get one right triangle, in which case the angle B is a 90-degree angle. And in case 3, if B sine of A is less than A, we get two triangles. So those are the situations that we're looking at. Those are the three cases. So the ones that would really matter about when we look at it is scenario 3, when we have an angle less than 90 degrees and side A is less than side B. We have issues. So let's go to some examples. Okay, on the assignment, you were told to find each measure using the given measures from triangle ABC. Here we're given side C is 38, side B is 34, and angle B is 36. This is one of our side angle situations that we're worried about. So I look at my angle. My angle is 36. That means we're already down in scenario 3. And when I look, the side opposite the angle, so that's the side B, is less than my other side. That means we're into case 3. So I need to take 38 times the sine of 36 and see how that compares to 34. Well, 38 times the sine of 36 happens to come out to be 22.3358, which is less than 34. Now, this is that third case scenario. I have an angle less than the side opposite. I have two sides and an angle, and the side opposite my angle is less than the other side, and that third side, the big side times the sine of my angle, is less than my side. So this is a two-triangle problem. So we can go ahead and set up the law of sines. So 34 over the sine of 36 would equal 38 over the sine of angle C. Okay, so if I solve that, I would take 38 times the sine of 36 and then divide that by 34. And that would give me the sine of angle C. So 38 sine of 36, we know is at 22 for whatever. So if I divide that by 34, I get like 0.656936. Now the reason that this comes into play is we are looking for basically the angle that resides right down here. I probably didn't show up real well. Let's go here. This is the angle we're trying to find. Notice in one case we have an acute angle. Well, when I do the law of sines, it gives me acute angles. However, there's also this obtuse angle that could come into play. And that's what's happening on our problem here. Is this right here is equal to our sine of C, and there could be two different triangles that are making that up. So here's how I figure out what those two angles are. The first thing I do is I go ahead and solve it. So the measure of angle C is the inverse sine of that number, 0.6569 ... Okay, so inverse sine of that number gets me 41.1 degrees. Okay, to the nearest 10, 41.1 degrees. Now, since there's an obtuse angle and an acute angle that have the same sine value, I take 180 and I subtract that number. That gives me the other option. So if I take 180 and I subtract that number, I get 138.9. If you take the sign of 138.9, it's going to be the same decimal again. We get 0.6569364, yada, 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 the same one we got. So what happens is we have two angles there for that problem. So what happens if we get a problem where we have to actually solve the whole triangle, not just find a missing angle, but solve the whole triangle? So we would use the law of sines if we're given two sides and an angle. So here I have three different problems. Oh, kind of got those hooked together. That was low, that's why I did that. Okay, so I got three different problems here. And as I look at these three different problems, I notice that they're all side-side angle problems. That's the only time we have an issue on the law of sines, if we're given two sides and an angle. So then what I do is I go ahead and run through my scenarios. Let me use the green. First thing I do is what side-side angle is, I look at the angle. Here, my angle Q is 111 degrees, which means it's more than 90. So as long as side Q is larger than side P, I have one triangle. So in other words, I just use the law of sines, and the answer I get will be the answer I get. No problems there. Okay, case number 2. I have an angle that is less than 90 degrees. Less than 90 degrees. That automatically sticks it into that third scenario situation. So then what I do is I compare the two sides, and notice the side opposite the angle, so the other P, is greater than the other side. So here again, I just get one triangle. Nothing to worry about. Law of sines is going to give me the answer. Third case scenario. Again, my angle is less than 90 degrees. And the side opposite my angle happens to be less than the other one. We are into case 3. So now I've got to take 40 times the sine of 33 and see how that compares to 27. 40 times the sine of 33. Oops. 40 sine 33, there we go, is 21.27. Sorry, 21.788 which is greater than 27. Sorry, is less than 27. So that means we get two triangles in this problem. So here's how we solve this triangle problem. We know we have to have an angle P, we have to have an angle Q, we have to have an angle R, we have to have a side P, a side Q, and a side R. So my P is 27, my Q is 40. And my angle P is 33 degrees. Those are the ones I know. So what I do is I do this. I go ahead and I set up the law of sines, knowing I'm going to be looking for two triangles. So I've got 27 over the sine of 33 having to equal 40 over the sine of Q. So I go ahead and solve this. 40 times the sine of 33 would then have to equal 27 times the sine of Q, so then I would divide by the 27, would equal the sine of Q. Okay, so 40 times the sine of 33 divided by 27 gets me 0.80687 equal the sine of angle Q. So the measure of angle Q is equal to the arc sine of this number. So I'm just going to use my calculator and do the arc sine of that number. And I get 53.8 degrees. So I'm going to write that down, 53.8 degrees. Now, the other option here is if I take 180 and I subtract 53.8 degrees. I got to do that again. I made a mistake. And I get 126.2 degrees. So I have a second option and notice what it kind of does is I'm going to create a table in which I have two of these running side by side. So now that I have that, I need to figure out the missing R's. So I have my yellow case, I have my blue case. In my yellow case, I'm going to take 180, and I'm going to minus the 33, and I'm going to minus the 53.8. And it's going to give me a 93.2. So then I can go ahead and work through the problem again, and I'm going to use the 27 over to the sine of 33. And then let that equal side R over the sine of 93.2. And I'll solve this. So 27 times the sine of 93.2, all divided by the sine of 33, will get me my R. So 27 times the sine of 93.2 divided by the sine of 33 gets me R to be around 49.5 to the nearest tenth. Okay, so now I also have to do this problem for the blue. I've got 180, and I want to subtract 126.2, and I want to subtract 33, and it gives me my other angle at 20.8. So now I'll set up my law of sines with the 27 over the sine of 33 equaling the R over the sine of, what did we just say, 20.8. And I solved that problem. So 27 times the sine of 20.8, all that has to be divided by the sine of 33 to get my R. So 27 times the sine of my 20.8 divided by the sine of 33 gets me an answer of around 17.6. So I end up with two triangles here that are my answer. Right there are my two triangles. And what I do is I just have to use those two triangles. So the first case, I run through it as if there was only one answer. I run through all the yellows. And then I go back, and because the first angle I found was the angle Q, I make sure I get that other angle right away, and I fill that in my table too. So those are my two solutions. That's that ambiguous case. Watch out for it.